and I'll take it away. We have Bangalore.
Yep, we're good to go whenever. It's
Okay.
recording now.
Oh,
So
okay.
welcome everyone. Oh, sorry. Okay. So welcome everyone to the 2024 Turing Award winner speaker series at the Georgia Institute of Technology, College of Computing, sponsored by AI2 Incubator. During the course of the semester, 5 Turing Award winners, 1 Nobel laureate in physics, and many other famous computer scientists will be speaking and giving presentations to 2,000 plus RSCP'd students and faculty from the top computer science universities in the world. Thank you very much to our esteemed speaker series advisors, Dr. Spiegelil and Dr. Bjarne Sestrop, for helping make this initiative a reality. I'm so grateful for your advice and guidance as we planned this tremendous speaker series. Thank you as well to our favorite LinkedIn influencer and sponsor, Aish Sarvizian, for her assistance in helping market the series to our 485,000 plus LinkedIn followers. We simply could not have achieved our stellar attendance numbers without you. I'm extremely excited to announce our speaker, the insanely accomplished computer scientist, Dr. Jeffrey Ullman. Dr. Ullman is an American computer scientist and the Stanford W. Asherman Professor of Engineering, Emeritus at Stanford University. His textbooks on compilers, various editions, popularly known as the Dragon Book, Theory of Computation, also known as the Cinderella Book, data structures and databases are regarded as standards in their field. He and his longtime collaborator, Alfred Aho, are recipients of the 2020 Turing Award, generally recognized as the highest distinction in computer science. Here are a few of the awards that he's won, and they don't even include all of them. ACM Fellow, Knuth Prize, IEEE John von Neumann Award, Medal, and the Turing Award. Dr. Ullman was inducted as a Fellow of the Association of Computing Machinery, and he actually was the PhD advisor of Sergey Brin, one of the co-founders of Google. So thank you very much for everyone that's joined. If we could give a massive, we're at 65 people right now. Let's give a massive virtual round of applause. Let's welcome Dr. Jeffrey Ullman. Let's go, guys.
Well, thank you very much, Zack.
Absolutely.
Okay, let's hope I can work this technology and actually share my screen and give you some, show you some slides. Okay, so let's hope for the best here. Okay. Again, I hope you can see the slides at this point. Is that
Yes,
true?
we are able to see the slides.
Okay, so what I thought I would talk about, look, everyone knows machine learning is a big, very important deal these days, and the point I'm trying to make is that there are still some very interesting algorithms, typically involving very large-scale data, that are not really machine learning. And I'm going to talk to you about just 4 examples of these today. You can see them listed on the screen. Okay, first of all, I don't mind plugging my book. It's free. It's published by Cambridge University Press, but you can get a free copy downloaded from the website that I have there. It's by Yuri Leskovich, Anand Radharaman, and myself. Okay, and the stuff that I'm going to talk about today is all somewhere in the book. Okay, so the first story I want to give you is what's called locality-sensitive hashing. It's really one of my favorite algorithms. It's a broad family of related algorithms, and I'm only going to be able to talk about one very simple example called entity resolution. But I'll try to give you a feel for what the general idea is. Okay. Marvin Minsky actually once said that you can tell a computer scientist about the fact that they believe that hashing is real. When you think about it, the idea that at least in expected time, you can insert, delete, and look up items in a set, no matter how big that set is, and it only takes a constant amount of time per operation, independent of the size of the set. That's kind of remarkable. I think locality-sensitive hashing is another one of these ideas that your intuition would be that it's impossible, but it, in fact, it is in fact possible. What locality-sensitive hashing does is it lets you find pairs of similar items from some large set of items. You could have millions, billions, trillions of items without ever having to look at each pair to see whether or not they're similar. Now, the notion of similarity, of course, is well, there are many different definitions, and it depends on the application. So, for example, if you're want to talk about similar character strings, you might say, well, they're similar if you can get from one to the other, making at most 10 insertions, deletions, and modifications of characters. Okay, or if they're sets, you might say they're similar if the size of their intersection is at least half the size of their union. Now, sometimes for some notions of similarity, it's really easy. And in particular, if a similarity forms an equivalence relation, then there's a very simple approach. So, for example, think of a deck of cards. And let's just say cards are similar if they have the same rank. So the ace of clubs and the ace of hearts are similar, as well as the other two. They're also similar to the other two aces. But they're not similar to anything that isn't an ace. Well, it's easy then to find the similar pairs without looking at each possible pair of cards. You just deal the deck into 13 buckets, 1 bucket for each rank. And then you'll find all the similar, well, all of the similar cards will have fallen into 1 bucket, so you can just find them very easily. And it takes no more time, really, than the number of similar pairs that actually exist. Trouble is, in most cases, similarity is not an equivalence relation, and so you can't use this bucketizing trick. So suppose, for example, that we'll say cards are similar if they agree either in the suit or their rank. Then you've got to throw the ace of clubs into the same bucket as the ace of hearts, yes. But the ace of hearts also has to be in the same bucket as the 4 of hearts. And so this is not an equivalence relation because it's a similarity relationship is not transitive. The ace of clubs is not similar to the 4 of hearts. So if you think about it, in fact, the only way to assure that each similar pair is in the same bucket is to throw all the cards into 1 bucket. So you really haven't done anything, and you then have to look at each pair in that 1 bucket and check to see whether they are similar because they have either the same rank or the same suit. Okay, well, again, as I said, locality-sensitive hashing is really a family of techniques, one for each definition of similarity. But in general, what you're going to do is you're going to have several different hash functions. And in my example, I'm going to use 3 different hash functions. But in practice, it would be typically hundreds or even in some cases thousands of different hash functions. And for each hash function, you have a separate set of buckets. And for each hash function, you take all the elements and throw them into one bucket for that hash function. That's just how hash functions work. And then we're only going to look inside the buckets and compare only the items that that appear within the same bucket at least once. And hopefully these buckets will be very sparse, so there will be very few. There'll be lots of buckets, very few items in a bucket. And so the work of looking at pairs of items that appear in a bucket at least once will be much less than the work of comparing all pairs. The advantage then is that if you design those hash functions correctly, and then, this is to an extent an art form, you will, the number of pairs within a bucket, within any bucket, is still a small fraction of all pairs. The downside, though, is that you could have a pair of items that are similar, but none of the hash functions throw them into the same bucket, and therefore they never even get considered for similarity. So again, the black magic here is you have to find suitable hash functions that have the property that if items are similar, there's a good chance they'll wind up in the same bucket. But if they're not similar, then there's a very tiny chance they'll wind up in the same bucket. It's not going to be 0 chance, but you want that to be very small. And again, you might just think, well, that's impossible, right? And if you use, the standard hash functions that you learn in the first or second course in computer science, those hash functions do not have these properties. But as I said, for many notions of similarity, you can find these hash functions. And I want to give you just a very simple example. The problem is called entity resolution. And the idea is you're given a set of records that describe, let's say, people. It could be any kind of entity, but let's say that it's records describing people, and that the records have fields like the name or the phone number, the address, maybe birthday, and you want to find you're going to say records are similar if they refer to the same person. Okay, now you might think this is an equivalence relation. The records are represent the same person if only if they have exactly the same name, exactly the same phone number, exactly the same address, and so on. But it's not because there are many different factors. First of all, there are people with the same name that are different people, or names get misspelled, or phone numbers. There can be typos in a phone number, or I might use my cell phone number in one record and use my landline. Yes, I'm an old guy. I have a landline, and I use my landline in another record. So the records refer to the same person, me, but the phone numbers are different. So the whole problem is again, it's much trickier than you might think at first glance. Now, if let's say 1 million records, which is these days not a very large set, the number of pairs is half a trillion, and if you have to compare half a trillion pairs of records, you got a lot of work to do. I mean, it's kind of feasible, but you know, on the other hand, say credit rating agencies that have essentially this problem of they get hundreds of millions of transaction records each day, and each one has a name and maybe a phone number or a social security number or information about individuals, and they have to figure out which person in the world a given record refers to. And 100 million choose to is just not something you can do today with a computer. So you have to use something like a locality sensitive hashing approach to even have any hope of being able to sort these records by person. Okay, so for this, for the entity resolution problem, it turns out that there are very simple hash functions. One hash function we could use is we'll throw records into buckets just depending upon their name value. So 2 records go into a bucket if they have identical name values. Now, if you look at a bucket for a given name, you hope that many of the records for a person will be in that bucket. For this, many of the records for a given person will, in fact, fall into the same bucket. But again, there are people with the same name, and their records will be in that bucket, and then yet the records are not similar. There will be typos, confusions. For example, when one record I might have just my first and last name. Another record I might have my first, last name, and middle initial, and they would go into different buckets. So it's we're going to have to discover that those records are similar another way. So another way we might do it is have another hash function entirely that is based on the phone value. So even if my 2 records don't have the same name, they might have the same phone number. And then we'll at least look at them and decide that they are the same, that they represent the same person. Well, we can have another hash function based on the address. And birthday would be a good thing if there were a birthday associated with records and so on. Okay, so what we're going to hope is that again, if records are similar, that is, they represent the same person, then they will have identical values and in at least one field. And we hope that if people are different, they won't accidentally agree in any field. And that turns out to be a pretty reasonable assumption. Again, remember that if two records appear in a bucket, then they are only candidates. They might still represent different people, and you should be able to tell that by the other field. So I might have 2 records with the same name. They have exactly the same name, but the phone numbers are completely different and the addresses are completely different. So they're probably different people who just coincidentally have the same name. On the other hand, well, maybe they have the same name and the phone numbers are off by 1 digit, and the addresses are different. Now, is this a typo? The person moved between the time those 2 records were created, but they're really the same person, except somebody made a typo of 1 character in their phone number. It becomes very, actually, this of course becomes a very tricky problem in itself. Anyway, just to summarize locality sensitive hashing, you take, at least for the entity resolution case, you use several hash functions based on things like the name or the phone number or the address, and you use some test for, are these records really similar, but you apply it only to pairs of records that appear in buckets at least once. And of course, hopefully you get only a small fraction of the pairs actually appear in a bucket together. But you will never look at a pair that, for small reasons like single character typos, don't agree exactly in any of the fields that you use as hash functions. And that unfortunately can happen. Okay. Well, the next story I want to give you is how to count distinct elements. Now, the model, I want to think of the data as coming in a stream. Could be a stream of search queries, let's say, or an example I'll give you would be logins to Facebook. But the problem then is we have elements in a data stream again, and they're chosen from a large set, let's say the set of all Facebook logins, all Facebook accounts. And I want to count the number of distinct elements that I've seen. Well, there's an obvious approach if you just maintain, just remember all the elements that you've seen. So just to give you a specific example, Facebook wants to produce a count of the monthly unique users. Now, Facebook, of course, has a lot of computing power and a lot of memory, so it can do something very, very simple. You just keep a hash table, and every time someone logs in, you check to see if they're in the hash table. If they are, then this is not their first login that month, so you don't do anything. If the user is not in the hash table, then this is their first login. You insert them into the table, and you increment the count by 1. And this works. Of course, it takes an amount of space that's proportional to, basically, you have to store the several billion users who are going to log in that month. Again, not a problem for Facebook, but it does use a lot of space. And I want to give you an example next where the hash tables themselves are pretty small, but there are so many tables you can't really store them all. Okay, and this problem is actually how web crawlers work. You start off, you want to find all the pages on the web, but you can't find all the pages on the web. Even all the static pages, there's just too many of them. So what are you going to do? You're going to start off with some trusted starting pages, and you crawl a page. The way you crawl a page is you report the page to the central repository where you're storing web pages, and you crawl it by looking at all the links inside that page, if there are any, and you put those links on a list of pages that should be crawled. Now, you might, first of all, you're going to do this in parallel. You'll have lots of crawlers sent out to the web acting independently, really. And maybe they'll report back say, trillion pages might be a reasonable number. But the web still hasn't been completely crawled. There are going to be things that are so far away from any of the starting pages that you haven't found them yet. But so you have to sort of start cutting this thing off, and you're not going to visit every page after you've gone out maybe 10 or 12 hops. So what you want to do really is visit the high page rank pages. These are the pages that might actually appear on the first, top 10 of somebody's search query. So you'd like to visit high page rank pages, but you can't really compute the page rank until you've got the web itself. So what they do is they just say, well, let's just count. We'll only crawl a page, let's say, if it has at least 10 predecessors, or the predecessors that we have found. And that's probably good heuristic. So what we have to do then is, for each page that we have reached but not yet crawled, is we want to keep a count of the distinct predecessor pages, and when that count reaches 10 or something, we will decide to crawl that page. Now, in this case, an approximation to the count should be satisfactory, because again, counting predecessors is just a heuristic for the best pages to crawl. Anyway, so instead of doing what I suggested Facebook would do, of just keeping a hash table with all of the predecessor pages for each of the trillion or so candidates pages, again, something that would take just way too much space. We can do something with just really a few bits that will give us a good approximation, and that's the real motivation for approximate counting. And so we're going to, and we will allow, there will be errors in the count. It's just an estimate of the count. We want it to be unbiased, neither uniformly too high or uniformly too low. But we want the accuracy of the count should go up the more bits we're willing to put against each count that we're trying to estimate. So there's an algorithm due to Flageolet and Martin. What you do is you pick, you're going to actually pick many hash functions, but I want to just talk about one hash function. And again, these are ordinary hash functions. All we need is that it maps, let's say if there are n elements in the universal set. Again, think of n as the number of Facebook accounts. You want the hash function to give you at least log n bits. Then for each of the for each element that might appear in the stream, we let R of that element A be the tail length, that is the number of trailing zeros. So for example, 000101 has a tail length 0 because it doesn't even end in 10. On the other hand, 101000 has a tail length of 3 because it ends in 3 zeros but not 4. And then based on this hash function h, and remember there are lots of different hash functions, but for each h you want to, what you record for that hash function is the maximum tail length for any element A that you've seen. And typically 5 bits should be sufficient because that lets you count up to 31. And there aren't going to be that many elements that that when you hash them, they end in 31 consecutive zeros. Sometimes 4 bits get you up to 15 consecutive zeros. That's probably enough. Now, the value of R, the maximum tail length, suggests that 2 to the R is a good estimate for the tail for the number of distinct elements that you've seen in the stream. Now, the intuition as to why this makes sense is if I've seen 2 to the R different values, then there is a good chance, it's actually 1 minus 1 over E, that I will have seen a value that has at least R zeros at the end. Okay. On the other hand, if you've seen many fewer than 2 to the R different values, the chances that you've seen one that has a tail length of length R is kind of small. Okay. The trouble is that reasoning is not quite right. Okay, because the expected value of 2 to the R is in principle it's infinite, and intuitively the reason this, at least for large R, when you increase R by 1, you have the probability of seeing that many zeros in a tail, but the value of 2 to the R doubles, so sort of every possible tail length contributes the same amount. So what you have to do, the problem then is really that you have to worry about incredibly large values of 2 to the R occasionally appearing. So again, we're going to use many hash functions. Think of it as hundreds of hash functions gives you very high accuracy. But even in the case of the web crawler, maybe even 3 or 4 hash functions might be fine. The trouble is how do you? Okay, so each hash function is going to give you an estimate of the number of distinct elements, and how do you combine them? Well, again, average doesn't quite work just because of the fact that expected value of 2 to the R is infinite. So you might get occasionally you get a very large value, and then you just will be way off. Median would protect you against the extreme values, but then you can only, since every estimate's a power of 2, you'd always be estimating a power of 2, and in fact, the true number of the true number of distinct elements might be very far from any power of 2. So what you do, again, the Flageolet-Martin approach is you group the samples into small groups and something like 4 log n, where n is, again, the size of the universal set. Again, think of it as the number of Facebook accounts. So you have many small groups. You take the average within each group. So occasionally there'll be some outsized element in the group, estimate in the group, and so that average will be dumb. But if you take the median of the averages, then you can get any number as a median because the groups are large enough. And yet you'll throw away the extreme those groups where there happens to be one extreme estimate that throws off that gives you an unacceptably large average. Okay. So next story is I want to sample a stream. So again, they're easy and they're hard cases. Let's talk about an easy case. Okay, Google wants to know how many times there was a search query for Taylor Swift. And but we want to save time, so we're only going to in the stream of all Google search queries. We're not going to take the whole stream. We'll take a random 1/10 of the stream. Better be random, not the day of the Super Bowl. But just as long as you take a random sample, you would expect to be able to count the number of Taylor Swift queries in the stream, in the sample of the stream, and then all you have to do would be multiply that count by 10, and that would be a fair, an unbiased, quite accurate estimate of the actual number of occurrences of Taylor Swift. So that works just fine. Now, this looks somewhat similar, but in fact, well, it turns out to be far messier. Now, what Google wants to do is find out in the past month how many queries were unique, in the sense that they were asked only once. And again, what we'd like to do is sample, say, 1/10 of the stream, and just look at that sample and try to figure out how many unique queries there would be in the whole stream. The trouble is that the fraction of unique queries in the sample is actually unrelated to the fraction in the stream as a whole. So you can't do something similar like, well, take the fraction, multiply by 10, or divide by 10, or something. Again, so if a query is unique, then it has a 1/10 chance of being in the sample. But suppose a query occurs exactly twice in the stream. Well, there's a pretty fair chance that exactly one of those two occurrences will appear in the sample. In fact, there's an 18% chance. So in the sample, not only queries, but also queries that look unique, and look exactly the same in the sample. They appear only once in the sample, but they really are not unique in the stream, and you don't know. It could be that every query is either or twice, or it could be that no query is asked twice. You just don't know, and you can't tell by looking at the sample. And then, well, of course, queries that appear 3 times in the stream have, I think, a 24% chance of being unique in the appearing exactly once in the sample. So it's a complete mess. And the mistake that we made is, what I suggested was we were going to sample based on the position in the stream rather than the value of the stream element. And we can do that. So the right way to sample the stream and answer the query, how many, what fraction are unique, is to hash the search queries at random into 10 buckets. And a sample then will be, let's say, all those queries that hash to bucket 0. Or it could be one of the others. It doesn't matter. But just the sample is just one of those 10 buckets. And the reason this thing works is because either all or none of the occurrences of a particular search query will be in the sample, and therefore the fraction of unique queries in the sample should be the same as, or should be a good approximation to, the fraction of unique queries in the whole, so that and that works. Well, you can do it if you're really concerned about about the sample size. You might want to say, well, I'll sample 1/10, but only up to 1 billion search queries. If we have more than 10 billion search queries in the whole set, I just want to limit myself to 1 billion. So you can do that too. You simply hash to a larger number of buckets, and you can pick more than one bucket as your sample. So again, let's assume we want 10%, but at some point we want to say, well, we just have, even our sample is too big. So say hash to 100 buckets. And initially I'll take 10 of those buckets, say 0 through 9 as my sample. But if the sample gets too big, I'll throw out bucket 9. If it's still too big, I'll get rid of 8 and so on. Hopefully, I'll still be happy if the sample is 1/100th. If I want an even smaller sample, then I got to hash to more than 100 buckets. Okay, so there's a simple generalization. The idea is you want to think of data as key value pairs. And again, the way to think about it, if you know SQL, the SQL, the query language, the key is going to be attributes that you want to group by. And I'll give you an example without going into the details of SQL. Now, in the example of finding unique search queries, the data actually was all key. And in general, you want to do your hashing based only on the key value, not the components of the data that form the value V. And then my sample will be the key value pairs whose key is in one of the selected buckets. So here's it's not a very simple example, but I hope you'll follow it. My data is triples of the form employee, department, and salary. And what I'd like to know is what is the average taken over departments of the range of salaries within a department. So for each department, again, think of if I wanted to query this, what I'd say is, well, I want to group these triples by department, and then within each department, I want to find the minimum and maximum salary, and take the difference. Okay, that's sort of what the query would be doing. So we're grouping over departments and not the other two attributes. So the key is department and the value is the employee and the salary. Now, if I pick random triples rather than random key values, then what would happen is I'd get some triples for each department, but again, thinking of a 10% sample, for most departments, I'd be missing the minimum or the maximum salary or both. And the errors would be biased to the low side. That is, the values that I get for each department would be could never be greater and would often be smaller than the actual salary range. On the other hand, if you do it the right way, you pick, you'll hash only the department, you'll pick some of the departments, and your sample will have all the salaries for the departments you picked and none of the salaries for the departments you haven't picked. So you'll get accurate for the departments you picked. You'll get accurate salary ranges, and hopefully the average of those salary ranges will be approximately the average if you took if you looked at all of the departments. Okay, last but not least, I want to talk about the problem of finding triangles in a large graph. And well, I don't know why do I care about this? Well, this may be a slightly lame argument. People who study social networks point out that there's a notion of a community, that is, people who share an interest, and the density of triangles is a measure of the maturity of the community. So the reason being that as time goes on, people in a community are going to tend to, they'll issue friend requests in terms of Facebook, so that they will tend to connect or follow each other if it's Twitter. But what I'm actually talking about, there's a recent theory of optimal join computation. And again, if you're not familiar with database systems, don't worry about it. But I showed you, here's, if I have an edge, if I represent my graph by an edges relation, that is, the edges relation is the pairs, the pairs of nodes that have an edge between them. You can just join edges with itself 3 times, and what you'll get will be all the triples of nodes that form triangles. And again, it turns out that in this general algorithm, of which finding triangles is just an interesting special case, you have to pay attention to the number of times a value appears in a column in order to compute the joins optimally. In this case, what it really means is, you want to know, what we care about is the degrees of the nodes. That's really the number of times the node appears in the edges relation. Now, I have to tell you a little bit about what I assume about the computation model. It's, again, nothing you wouldn't have learned in your second class in computer science. I want to assume that in constant time, I can determine whether an edge exists between 2 given nodes. So I can just say, put the edges into a hash table. At least in an expected time, it's just constant to tell, given 2 nodes, does their edge exist? But there's something else I need. I need to know that given a node, I can find its adjacent nodes, again, in time that's proportional to the number of adjacent nodes. And I can do that, for example, by, in addition to the hash table, for each node, I have a linked list of its neighbors. Okay, so I'm going to say this is a big graph. It has n nodes and m edges. Of course, the number of edges m can't be more than n choose 2, which is a little even less than just a little less than half n squared. So m is never bigger than n squared, and often, especially let's say in a social network where the edges are, it's kind of a sparse graph. The number of edges is m would be maybe a few hundred times n, and n might be a billion. Well, one algorithm for finding triangles, just consider all triples of nodes and use that hash table to just find out in constant time whether there are edges connecting all 3 pairs of those 3 nodes. So that's again, there are n, roughly n cubed over 6 different triples of nodes, and takes constant time to do each. So it's an order n cubed algorithm. A somewhat better approach would be take one loop over all the edges E and another inner loop over all the nodes U, and then simply test, again, using the hash table, whether U has edges to both ends of E. And if so, U and the edge E form a triangle. Now that's, again, there's one loop of size M and one loop of size N. So it's an order Mn algorithm. And again, since M is no bigger than N cubed, and it's often less, this can't be worse than order N cubed, and again, in many times is better. So is that the best you can think of? Probably is, but there is a better way. And that requires something called the notion of a heavy hitter. And would define a node to be a heavy hitter if it has degree at least square root of m, square root of all the edges. Okay, so there's going to be a heavy hitter is going to have very high degree. Again, if you think about the Facebook graph, a heavy hitter would have, I don't know, about 40,000 degree around 40,000. So it'd be somebody who has 40,000 friends. Not going to be too many of them. And in fact, there can't be more than 2 square root of m heavy hitters, no matter what the graph is. Because remember, each edge adds 2 to the sum of the degrees. It adds 1 for each of its ends, to the degree of each of its ends. So the sum of the degrees is always 2m. And so you can't have more than 2 square root of m heavy hitters. Now, we're going to find heavy hitter triangles in a special way. That is, a heavy hitter triangle has all 3 nodes are heavy hitters. So I'll use the first what seems to be the dumbest algorithm, but only for the heavy hitters. And I'm all of heavy hitters and check to see if there are edges between each of the 3 pairs of nodes. And again, since they're order square root of m heavy hitters, this takes time at most order m to the 1.5. Now, the other triangles, of course, will have at least one node that's not a heavy hitter. So what I'm going to do is I'm going to loop over all my edges. And for each edge E, well, if both are heavy hitters, if both ends are heavy hitters, then I'm not going to worry about it. I'll just do nothing. But if at least one end node is not a heavy hitter, then I will find one of those. If neither is a heavy hitter, then I can pick either. It doesn't matter. So node U is one of the ends of E. It's not a heavy hitter, so it has degree at most square root of m. And I can use that linked list for U to go down the list of neighbors V, and I'll just check whether V is connected to the other end of V. And so that also takes time order m to the 1.5, because you have one loop for the edges. And the inner loop now takes order square root of m time, because you're just chunking down a list of at most length square root of m. So you have there are 2 different algorithms that find triangles of 2 different kinds, but together they find all the triangles, and they both take order m to the 1.5. And by the way, this is the best you can do, because I won't go into it, but you can, for any reasonable n and m that could form a graph, you can find a graph with n nodes and m edges, and it has big omega of m to the 1.5 triangle. So you can't do better than that, simply looking at algorithms measured by n and m. On the other hand, m to the 1.5 is never bigger than n cubed, and in fact, never bigger than m times n. And in the common case where m is much less than n squared, m to the 1.5 is much less than m times n. Okay. I'm not going to go into this, but you might think about this. You don't want to double count. Okay. And in particular, the non-heavy hitter triangles. Let's say if 0 or 1 of the nodes in a non-heavy hitter triangle are heavy hitters, then it seems you'll find that triangle looking at each of the 3 edges. If 2 of the 3 nodes are heavy hitters, then you only find it twice. So you have to do a little adjustment to get the exact count. And I'll leave you to figure that. Okay, so with that, I'm going to stop sharing, and I guess there may be a little time for questions.
Now we're just going to do a quick conclusion.
Okay.
Yashir Koach, Dr. Ullman, thank you so much for taking the time. Thank you so much for taking your extremely valuable time for this extremely insightful presentation. Can I get a massive virtual round of applause from the audience? Come on, guys, don't be shy. Okay. And we actually have, it looks like we have some questions.
Sure.
Audience, people are raising our hands. Is that the case?
Good. Well,
if you have a question.
Well, I see some hands raised.
Yeah, I saw some hands raised. I don't know. If you have a question, if you want to put it in the chat. I wasn't sure.
All right, let's see. Okay, I can look at the chat.
Yeah. So anyone, if you have a question, guys, please put it in the chat so that we can see what it is. And I saw some hands raised. I wasn't sure. Maybe that was their way of applauding. Okay. Okay.
Okay. Oh, okay. I see they're dropping questions. Let's think.
Yeah. Okay. Okay. So yeah, it looks like.
Where can we view the recording? I guess you'll have to. That's what.
Yeah. Okay. So, Dr. Ullman, thank you so much for taking your extremely valuable time to educate us students. I will be following up with you shortly to inquire where we can send you Godiva chocolates. We would like to extend our deep appreciation for your time and your willingness to speak with us. And thanks as well to everyone in our audience for your attendance. And we'll see everyone next week. We're going to have Asaf Schuster. And then the week following, we're going to have Jack Dungara. So really appreciate everyone attending. And Dr. Ullman will be following up with you soon to send chocolates for.
Okay.
Thank you so much for your time.
Oh, well, thank you very much. Glad I had a chance to spread the word, as it were.
Absolutely. All right, guys. Thank you so much. Everyone have a great rest of your week.
Okay.
Okay. Bye, everyone.